where I investigated a ball as it fell onto a spring. Okay, so first we have the introduction and main physics principles we used in this lab. Okay, what was this lab's purpose? Well, I wanted to analyze the motion of a ball as it fell into a spring and compressed it, and then I wanted to use this to determine the spring force constant of that spring, using the energy principle and other ideas we learned in class. The problem we chose to solve was a ball of mass 15 kilograms that is dropped from a height of 3 meters and then compresses a spring to 1 meter before coming to rest. To then find the spring force and compute the spring force constant of the spring, we use GlowScript to create a model of this exact situation as a ball fell onto and compressed a spring. The fundamental physics principles used were the energy principle, which states that the change in energy is equal to the work done by the surroundings, which is also equal to the change in kinetic energy, the change in gravitational potential energy, and the great change in spring potential energy, which are the energies we'll look at today, specifically the potential energies. And we also use the force equations, which in this model were the spring force and gravitational force equations. And then we also use the position and velocity update formulas to update the position of the ball as it fell and touched the spring. What were these labs' results? Well, we were able to find the spring force constant by entering the values from the problem into our model, and because of this, we knew that the energy principle was satisfied as our values aligned with the actual solution of the problem. So, modeling the experiment, we have to define our system. And when we do this, we assume that there are no other forces acting on the ball besides the gravitational and spring force, so no drag or friction on the spring. And then defining our systems, we know that the ball, spring, and earth are in our system, and the surroundings could include anything else happening possibly in the model. Okay, so our free body diagram shows that before the ball touches the spring, the only force acting on the ball is gravity. However, when the ball does touch the spring, gravity is still pulling it down. However, there's now a new force, the spring force, pushing the ball back up as it becomes compressed. Okay, next, looking at our computational model. First, our initial conditions from the problem introduced were that the mass of the ball is 15 kilograms, the initial position is just in the y direction at 4 meters, the initial length of the spring is 1.2 meters, the final length will be 1 meter as it's compressed, and then time, we're starting at 0, and our delta t, or dt, is 0.01, and that's going to be how we change the time. And the rest just establishes the floor, the shape of the spring, and the shape of the ball in our world. And we also can find k by solving for it by setting the gravitational potential energy equal to the spring potential energy and solving for k, as we see here. Finally, we have our final conditions, which are split up into phases 1 and 2, because we first have to model the ball's motion before it touches the spring, which we see in phase 1, where the net force is equal to just the force of gravity, which is then plugged into the velocity update formula to find the velocity, and then that velocity is plugged into the position update formula to model the ball's position and motion as it falls before it touches the spring. Phase 2 is after the ball touches and hits the spring, and first we have to find the final S, or compression of the spring, which we do by again setting the gravitational potential energy and the spring potential energy equal to each other and solving for S. We do this to find the final stopping position of the spring to stop the program entirely, as we see at the bottom of the program. We then have to find the second net force. However, this time we have to include both the gravitational force and add that to the spring force. Then we plug this new net force into the velocity update formula again, which we then plug back into the position update formula to then model the position of the ball as it falls. Finally, we have our discussion and conclusion. So our model looked like this. In here, we see the ball falls, and the ball does compress the spring, and we also find that the model gives us the spring force constant at 1,176 newtons per meter. Model errors. Well, because our model is based off of an ideal problem, there might not be any errors in our actual model. However, if we were to compare this to a real-life scenario, we would have to then include forces such as drag, air resistance, or dampening on the spring, because obviously there would be more forces acting on the ball in real life. Concluding questions: what does this mean? Did our model actually accurately predict the spring force? Yes. When we look at the actual solution to the problem, we see they also got 1,176 newtons per meter by using the same equations we did. What if we change the mass of the ball, and would the amount of the spring compressed change? Well, if we change the mass of the ball from 15 kilograms to 10 kilograms, we see that the S, or the amount compressed, would change. It would go down. This is because the gravitational potential energy is directly proportional to the spring potential energy. So if mass decreases, the S decreases. Thank you.